images, forming images through lenses and mirrors. So it's produced by either refraction of light or the reflection of light through a lens or a mirror. You can get real or virtual images. Real images are where the light rays actually converge where you see the image. Virtual images are where the light rays don't actually converge there. It's kind of a trick of the brain, is how I like to think of it, at least. The simplest version is a plane mirror. It's perfectly flat and smooth, so the reflection angle is exactly the same as the incoming angle, and it forms an image. It appears to me that my image is back behind the wall. If I'm staring at a mirror on a wall, it looks like the version of myself that I am seeing is behind the wall. That's because the light rays bounce off of, let's say, my hair and back to my eyeball. Of course, my eyes are not used to the idea of light either bending or bouncing, so it assumes that the light ray had just traveled straight the entire time, and it forms an image back behind. This would actually be a virtual image, because the light rays are not actually converging where this image is formed. In fact, they couldn't. There's a wall there. But my brain believes it does, so that's a virtual image. Now things get a little more complicated when you start dealing with lenses or mirrors that are curved. This is what's called a ray diagram. Basically, if I take an object and I pick a point on the object, let's just say the top of it for simplicity, there are going to be rays that are going off in all sorts of directions, and it's kind of crazy, but all we need to do is focus on 3 distinct special rays. The first ray comes off the object, travels parallel to the principal axis, hits the lens, refracts, goes through the focal point, and continues on. Another ray comes off the top of the object, goes through the focal point on the other side of the lens, closer to the object, hits the lens, comes out parallel to the principal axis. And the third goes from the top of the object through the very center of the lens, because of its angle, does not refract, and continues on straight. Where these 3 rays intersect, that's where the image is going to be formed. With mirrors, it's a bit of a different story. You've got one of these rays, called a principal ray, parallel to the principal axis. It reflects off the mirror, goes through the focal point on the same side as the object, as the mirror, and I've got another one that goes through the focal point first, comes out parallel to the principal axis. Where these 2 intersect, that's where an image is formed. Oh, and by the way, that's a real image because the lines are actually intersecting there. Here's an example of a diverging lens. It is concave rather than the convex version that I showed you of the first thin lens. I've got a principal ray that travels, it's parallel to the principal axis, strikes the lens, and it travels up instead of down. Now, again, the human brain likes to backtrack it. It assumes light always travels in a straight line. So if you backtrack away, it goes through the focal point, even though it doesn't really. Diverging lenses are crazy. So the second ray would be heading to the second focal point, except it strikes the lens and it comes out in a straight line, parallel to the principal axis. Backtracking, it intersects with that first imaginary part of the ray that I drew. And finally, I've got one that just passes straight through the center of the lens. Where these all converge, that's where a virtual image is formed. Virtual images and diverging lenses are ridiculous, but they just follow the exact same equations as converging. Here I've got a little simulation courtesy of Minute Physics to show us how lenses work. Here you'll find a thin lens. This is similar to what you have on your eyeball, similar to what you'd have on a camera. Here, you've got some guy looking absolutely fly. He's what we're going to call the object. The object is whatever's really there. Here, you're going to see a little screen. This is where the image is formed. For your eyeball, it's the back of your retina, but for right now, we're just going to treat it as a little screen here. And for the purposes of the simulation, you'll be able to see what the image will come out as over here. Currently, we're just focusing on rays coming off of this guy's head. But I could change it. Let's say his bow tie. I want to see where the image of his bow tie will be formed. Now I've got light rays coming off of the original bow tie, going through the lens, and forming the image of the bow tie on the screen. Or I could do it for his shoes. Doesn't really matter. All that matters is that all these principal rays are seen relative to the principal axis. The principal axis goes directly through the center of the lens, like so. He's got one ray that comes off his head, and then goes through the focal point. You can see the focal points here and here. One ray comes off of his head, bends through the focal point, and then strikes the screen. Another ray goes through the near focal point, strikes the lens, and comes out parallel to the principal axis. And finally, one ray passes straight on through and strikes the screen. Where these three rays converge, that's where a sharp image is formed. Now, what if these three rays don't converge there? Let's say I move this guy a little bit closer, and now the three rays are not converging on the image screen. The image gets all sorts of blurry. Or I can move him farther away, and the image gets all sorts of blurry that way too. That's because the screen is no longer at the location where the image is being formed. The image would be formed here. In fact, if I move the screen closer, then the image comes into sharp focus once again. The location where the image is formed depends on the distance of the object to the lens and the focal length of the lens, which can be measured on either side of it. From the thin lens equation, I can solve for the image distance, and that'll tell me where I need to place my screen. But wait a second. If this is how your eyeball works, and the image is formed on your retina, I'm fairly certain you're not moving your retina forward and backward. You can focus on objects near you and focus on objects far away from you, but you're not moving your retina. So how can you possibly focus on objects at different distances without moving your screen? Well, one way is to change the shape of your lens by having it bulge out more or compress. So you actually have little muscles on the top and bottom of your lens that can squeeze it down and bulge it out, or stretch it up and make it thinner. By doing that, I can focus on images that are farther away, and images that are farther away appear smaller to me, or I can focus on images that are up close, and images that are up close appear a little bit bigger. By bulging out the lens or thinning the lens, all I'm doing is changing my focal length. You can see those little focal points moving backward and forward there. So that way, for a different object distance, I can change my focal length and produce an image on my retina just the same. This is why you won't have everything in your field of vision in sharp focus. If you're looking at something close to you, objects in the background appear blurry, and if you look at objects in the background, objects close to you appear blurry. That's because your focal length has changed, but the image distance has not.